Okay, so now as I said, I am going to be discussing a little bit about the code itself. In this video, I am going to sort of use it more to sort of explain a little bit about how the Cocotb interface works, right. So by itself, this is not going to be talking about the AXI bus protocol. That will be the next portion that we are looking at. But what I want to show is, for example, how I could write a simple piece of code, how I could simulate it in Verilog, and how I could do the similar kind of a thing using the Cocotb test bench. Now you might find at this point that Cocotb actually looks more complicated than just writing your test bench in Verilog, but as your design gets more complicated, Cocotb's power really comes out over there. So let's try and understand what exactly is happening out here, right? I am writing a module. It's a parameterized module, right? You can see that the width is 8 bits, and basically what that says is, there is a register of 8 bits width, which I am calling Q, which is the output of this counter, okay. The counter also takes these 3 inputs. One of them is a clock. There is an active low synchronous reset. Once again, this is convention, right? RSTN, if I end with the letter N, it usually indicates an active low reset, right? And if I don't have the N, then it's usually indicative of an active high. Please try and follow those conventions. If you change that around, it can be very confusing when you're trying to interface with somebody else's code. Okay, so the code itself is very straightforward, right? There is this module, the always at passage clock. If the reset is low, in fact over here I don't even have a or negedge reset in, which means that this code is actually using what's called a synchronous reset, right? Just to sort of recap stuff from the DSD Digital Systems Design course. So this is a synchronous reset. If I had given passage clock or negedge reset n, then that would have been an asynchronous reset. It doesn't matter. Once again, both are in general compatible with what can be implemented on FPGAs and so on. But for our purposes, the important thing is the moment the reset is low, I set the Q to be the value 0, right? Else, if the enable signal is high, I increment Q. So this is a very simple kind of counter, okay. Alright, so how will I test that this counter actually works? So what I am going to do is to first show you a test bench that is written in Verilog. So this is a typical test bench that you might write for testing a counter in Verilog, right? You might write it slightly differently, but this is sort of what we have been following in earlier test cases. So hopefully this looks familiar to you, right? We have the module which we call in this case counter underscore TB. I use a parameter once again so that I can actually change the parameter and do the testing in a systematic manner. I declare registers over here for the clock, reset, enable, so that I can assign them within my initial or always blocks and use them in order to control the signals that are sent into the DUT, the device under test. The DUT instantiation happens over here. I basically map the clock, the reset, enable and the Q, and because this Q is coming out of the DUT, it has to be declared as a wire. Once again, in general, the preference would be to use system Verilog, in which case everything just becomes logic and we don't have to worry about wire at all, okay. Alright, what does my test bench look like? I start off by basically modeling a 100 megahertz clock. Keep in mind that this is only a model of a 100 megahertz clock. Just because I wrote code like this doesn't mean my software actually works at 100 megahertz, or rather my hardware actually works at 100 megahertz, right. But the way that the clock is modeled is, I start off by initializing clock equal to 0 and then every 5 nanoseconds inverting the clock. And then I basically say also, I want to dump out the data coming out of this simulation into a VCD or value change dump file. If you have mostly done your simulations on EDA Playground, you may not have actually used a VCD much, but that's also there. I mean, in EDA Playground also the VCD file is used in order to view the waveforms of the intermediate results that we have, right. And as you might recall, right, dump vars, what I am doing is basically dumping everything that's present in this test bench, right, because I might want to view it and see how the system behaves. All of that is sort of the setup for the test bench. The actual tests begin out here. I start off by initializing the reset to 0 and enable to 0, hold reset for a few cycles. Remember, it was a synchronous reset, so I need to make sure some clock edges have passed to ensure that the clock itself is actually ticking. Now there is one aspect that I want to sort of mention briefly over here. You will notice that I am going on looking for neg edge of clock over here, right? And part of the reason for that is because I am setting values such as reset equal to 1. If I had waited for pause edge clock, then I would end up with a race condition. I could potentially end up with a race condition. What I mean by a race condition is something where the pause edge of clock in the test bench and the pause edge of clock in my DUT are effectively happening at the same time, but as far as the Verilog simulator is concerned, it could do them in either order, right? And sometimes as a result what happens is, it does, because of the fact that these two are separate Verilog modules, the simulation sometimes gets into a wrong state and it does not actually handle them in the way that we would normally expect. In other words, as properly finishing up all the passages before coming back and doing the transitions on the reset. Okay. By changing my transitions to be at neg edge, it's not that I am actually saying that neg edge is better in some way. In fact, in general, when you are building a real system, the one thing to keep in mind is there is almost never a good use case, or rather very rarely a good use case, where you should be using pause edge as well as neg edge in your digital design. If at all you find that you are using both pause edge and neg edge in a design, you need to be very careful and look at your design to understand why that was required, right? So I just want to emphasize that the neg edge over here is being used to ensure that my transitions of reset and various other signals happen well before the next pause edge in the DUT. That's the only reason why I am using neg edge. Okay. So please keep that in mind. This is not sort of a recommendation to use neg edge in your designs, but in a test bench it actually makes sense to use neg edge because it ensures that whatever you are changing is going to be changed at a point in time which is well before the next pause edge which is going to be seen by the DUT. Okay, so I have reset the system. The first check or test that I can do is to check that the result after reset should be 0, and if it is not 0, I basically will give an error and straight away stop the simulation at this point. Now I turn on the enable signal, I set enable equal to 1 and I wait for 5 cycles. Remember that I am going with the neg edge of clock, right? So I would basically wait for at neg edge, which basically means that as far as the DUT is concerned, after I have set enable equal to 1, I am going to see 5 positive edges of the clock, okay, which means that my count at this point should be 5. So I check whether it's equal to 5. If it's not, I say expected Q equal to 5 but got something else. I can disable it, right, and ensure that it does not change, right? I wait for one clock edge, the thing should not have changed. Then I once again wait for another 2 clock edges, once again it should not have changed, right? Then re-enable it, wait for 2 clock cycles and check that it actually did change, okay. So as you can see, if I was writing out all of this code, if it was on EDA Playground, I would probably use the iVerilog simulator, add the test bench as well as the code, click simulate and everything is done and I can in fact view the various waveforms and so on. If I was doing this by hand instead, right, I would probably use a command like iVerilog and give the different commands that need to be run in order to actually get the simulation performed. Instead, what I am going to be using over here is, there is what's called a Makefile, which actually speaking has nothing to do with Verilog. A Makefile is something that is used for guiding the process of compilation, and in fact most of you would have come across the Makefile in embedded C, where we actually use it in order to compile C programs, right, or either the C code or the introduction to C programming or the embedded C programming, where we use it in order to compile C programs. So why am I using a Makefile? Well, one of the reasons we are using a Makefile is because Cocotb works very well with Makefiles. It in fact takes care of, a lot of the background is taken care of automatically by just using Makefiles appropriately. So I have that Makefile which is there for Cocotb, but in my case, as far as the test bench itself or the Verilog test bench is concerned, you can see that I have this way by which I can basically just run this command iverilog tb/counter tb.v rtl/counter.v -o tb.vvp and actually run the Verilog simulation. So in other words, if I just use this Makefile and I typed in the command make tb, it would run this entire simulation for me. So let's try that, okay. So there are a couple of warning messages that we need to actually get rid of, but anyway, just ignore them for now. What is important is this line that says building the Verilog test bench, it runs the iverilog command, running all of these messages, right. By the way, this iverilog building Verilog test bench, you might have seen, you might have noticed are actually being printed out in the Makefile, right. And it actually runs the Verilog simulation using the iverilog simulator, dumps the VCD, and in this case, because my counter was very simple and my test bench was also correct, it passed. Nothing there to really fail, right. It passed the entire test bench and it has dumped out the counter. So I am now going to open that with this program called GTKWave, right. So one thing to keep in mind is, as far as things like GTKWave and so on are concerned, this requires you to have, it is perfectly encouraged to try and install it on your own systems. It will not work if you have only sort of shell based access to a computer or to a Linux computer. You need to have the ability to actually display graphical output as well. Having said that, Verilator, iverilog, GTK, Cocotb, all of them work on Linux. They work on Windows subsystem for Linux, which means that if you have a Windows laptop, you can probably get WSL working. And as far as I know, they also work on the Mac, right. So these are fairly generic software, they are all open source, you should be able to get them working, and I would encourage you to sort of play around with them. For the most part, as far as the course is concerned, I will be giving demonstrations, but obviously in order to learn, you would need to try. The best way to learn is to try out making changes on your own. We will try and see what changes you can do by means of some kind of remote access simulators, but the GUI based simulation and especially the waveforms will be difficult to provide. So I strongly recommend that you try and get them running on your own systems. Okay, so now that I have the output which was in this counter tb.vcd, I am going to open it up with GTKWave, and what happens is that it brings up this picture where I can click on this and import all the waveforms that are present into my waveform viewer. It looks a bit strange, right? Nothing seems to be happening, but that's because it's zoomed in heavily. So what I'm going to do here is click on this zoom fit, and now you can suddenly see that a lot of things basically show up. There are some unnecessary signals that got brought in. For example, the width parameter shows up as a signal. It's not something that you are going to change, so we could probably have been a bit more selective about what we imported, but that doesn't matter. What is important is I have a clock. I can see that the enable signal goes high and then it goes low and then it goes high again, right? And corresponding to each of those, notice that the enable signal goes high at the negative edge of the clock, just like the reset also was removed at the negative edge of the clock, right? What that means is that at the next positive edge, the queue starts counting, right? The counter actually starts counting, and therefore I see that it changes to 1, 2, 3, 4, 5 and so on. When I change the enable back to 0, it stops counting. So at the next positive edge after that, there is no increment in the counter value. Once again I make this high at some point and I can again see that the output started incrementing. So these were all the test cases that we actually ran as part of the test bench, and sure enough it passes everything very cleanly. Okay. So as I said, this would be how you would create a test bench using pure Verilog. Now let's look at how I would do something like this in Cocotb, that is the Python interface. Okay. Again, the expectation is not necessarily that you know a lot of Python programming. What I will be doing is basically describing enough of the Python over here to sort of give you a flavor for how the test bench is written, right. But for the most part, we will be working with fairly standardized test benches. The reason why I am using Cocotb over here is especially when we need to interact with the Axie interface, it is much cleaner and a much more powerful way of actually connecting things together. So let's look at what the same test bench would look like in Cocotb, right. As you can see, this is a Python file, right. What happens over here is it basically starts a clock, performs reset, drives inputs, waits for the falling edge for the same reason as what I explained in the case of the Verilog test bench, and it also uses Python assertions to check that the conditions are actually passing as expected, right. So as you can see, what I am doing over here is, this is Python code, right. It basically says, okay, import Cocotb, which means bring in all the Cocotb functionality. I also bring in a module called clock and the falling edge. All of these are part of the Cocotb library present in Python. Now there are certain things over here that even are not part of regular Python. In particular, there is this notion of what's called an async function, right. And the reason why we need to use these things called asynchronous functions is, if you think about what a test bench is trying to do over here, it is actually trying to model multiple different Verilog modules all at the same time. And in this case, I have a Python code which needs to interact with a Verilog module. The Verilog module has a notion of time. It actually has a clock that needs to pass, right. So there is some increment in the notion of a clock, and every time that the clock reaches certain values, the Verilog changes its state. Now I need some way of simulating this in Python. Python by itself is a language like C. It does not have a notion of a clock. There is no concept of a clock inside C. There is no concept of a clock inside Python. Instead of that, what we do is we basically say that these functions which are defined as async, they are asynchronous, meaning that the function starts and it can then wait for input from another program, which in my case is my Verilog simulator, right. So what happens over here is, the reset function that I am defining will basically say, okay, I am going to asynchronously run this function. What it will do is set the value of the reset, as you can see, that is defined as dut.rstn.value, set that to 0, set the enable to 0, wait for 2 clock cycles. In Verilog, we basically gave repeat 2 at neg edge of clock. In Python, we are actually writing it like a Python code. I run a for loop which runs up to 2, right, and I use this, again, a new keyword called await. So async and await are two new things that are used in Python in order to emulate this behavior, where the Python code and the Verilog code can sort of talk to each other even though each one is progressing at a different rate. Okay. Now for the most part, for Verilog simulations, you do not need to understand exactly what is happening on the Python end of things, right. We will be using standard test benches. The reason why I am explaining all of this is just so that there is, you can get a flavor for what is going on, but you do not need to actually go deep into how exactly Python works or how Python coroutines, as they are used over here, work, right. We will mostly be using standard test benches for the important things that we are going to do, right. You could also rewrite all of your test benches using plain Verilog. It's just that it would be a little bit more complicated to actually get the thing working, right. So in any case, what is happening over here is, I wait for 2 falling edges of the clock, I then set the reset value to 1, wait for 1 more clock edge, and then this function is done. The interesting thing is, what I have done is sort of like defining a task in Verilog, where basically I have defined everything that corresponds to setting up a reset. I don't need to use an initial block. I can just basically at some point in my code say await the reset function, and it will take care of setting the value, advancing by appropriate number of clock cycles, and finally returning control back to me. Okay. I also define one more function called tick, which I can use in order to wait for any number of clock cycles. Okay. And as you can see, by default, if I just call tick, it will wait for one clock cycle. Otherwise, it will wait for whatever number of cycles that I have specified by just running a for loop over there. Now, the main part of the test comes in these functions, which are defined as cocotb.test, right. Once again, these are similar like Python functions. The first one is a basic counting test. It checks that the counter increments when it's enabled and holds when it is disabled, right. What does it do? I start this off inside the test case. So, this is sort of like actually having a full test bench in Verilog, right. I create a test case where I say, I am going to start a periodic clock. This notation start soon and so on is fairly standard. Like I said, you don't need to go into the details of why it is written in a certain way. This is the standard way by which a clock can be set up in Cocotb. But after that, here comes the interesting thing. I can just call the function that I defined earlier, reset. And this assert basically tells me, look at the value that is there in Q, convert it to an integer before looking at it, because after all, the data types that are used inside Cocotb are different from integers. They are actually some bit values. So, convert it to an integer, check that the value is 0. If it is not, then complain, basically print out this message saying that after reset Q should be equal to 0. Instead of that, I got this Q dot value. Okay. So, this assert is a very simple and powerful mechanism. It basically allows you to just specify what should be there, and if it is not, print out a message. Okay. Now, I can enable, wait for 5 clock cycles, assert that the value should be equal to 5, disable, check the current value, right, store it into a variable called snap, wait for 3 clock cycles, and check that the new value of the counter is still equal to snap, that is, it has not changed. If it has changed, then you can basically print out a message saying it changed while enable was equal to 0, the test failed, right. And then once again re-enable, right, wait for 2 clock cycles, assert the output, right, that basically we have this whatever was the last snapshot plus 2 because I waited for 2 clock cycles, and if it gave something different, say that it did not increment correctly. So, all of this is captured as one test case. The interesting thing is I can also write another test case which basically says set the basically wait for one tick value and then check that the Q value was equal to 1, right. We could also do this separately by making it count for a large number of clock cycles until it actually wraps around. There are a couple of different ways in which you could write tests. The point is to sort of illustrate that number one, Python can be used in order to write tests that are very similar to Verilog. So far, if you really think about it, the Verilog probably looked a little simpler, right, because Python has actually more code over here in order to get the same thing done. But as we will see when we get to the AXI, that is when the power of Python comes in. I can basically write very simple code in order to get the functionality of the AXI handshaking happening. Okay. So, anyway, how do I run a test like this? I would just run make, which by default in this case is actually going to run the Cocotb test bench. Now, one problem with that is by default this thing prints out a lot of information. So, I am sort of making the screen a bit more compact, and then I type make, it goes ahead, compiles all the code, right, appropriately, and then runs through and prints out a whole lot of messages. So, you can see that unlike the Verilog, this Cocotb has actually gone ahead and printed out a lot of messages that I did not actually ask for, right. It gives me a lot more information, but on the other hand, as far as I am concerned, the main important thing is it tells me which test it's running, the counter basic testing and the counter wrap example, each of those, the first test and the second test, it sort of shows me that each of them was run, each one resulted in a pass because none of the assertions failed, right. How much time did it take to simulate each of those, and finally how many tests were there, how many passed, how many failed, and so on. Okay. So the point is exactly the same functionality, slightly more verbose output giving me like more information out here, but as I said, this is all a setup for how we can do it with the AXI later. I can once again also open up the output that comes from GTKWave, right, and in this case it looks slightly different. It has actually put all the counter related values alone over here and created another module, right. You can see that this root IO is a separate set of signals that is part of what is created by Cocotb. The counter has exactly the same behavior as what we had in the previous case, all the different kinds of things that we have. Once again we reset and get it back because we are going over to the next test case in this thing, right. So you can see that I have a reset, then pull out of reset, run the entire test, once again reset, run the second test. Okay, so all of that gets taken care of automatically. So just to recap quickly, right, we will be using Cocotb for our subsequent test cases primarily because it makes testing AXI based interfaces a bit easier. And the purpose of this was basically to show you how it can be used in the context of a very simple example like a counter, but the same thing can also scale to larger systems.